So I'm going to show you how to do a simple linear regression with diagnostics of the fitting parameters using the GNU scientific library. It's sort of like a script you do in Python or R, but this is done in pure C using the GNU scientific library. First of all, in the code here, I'm putting the disclaimer here of the GNU license or the GNU General Public License because the code comes from the GNU Scientific Library, and if you distribute this code or if you use this code, you have to put this here, okay? So for this code to work, you have to have the GNU Scientific Library installed like I showed you in the previous video. This here in blue, as you should know, as you might know, are just comments in the C code. And this here is what you need to do to put in your terminal if for your code to run. So, and it is just reinforcing you have to have the GNU Scientific Library installed for this to work. This is explained in my previous video. I'm gonna get around to create a make file for that, but I just didn't have time to work on that. So the code starts here. Here are the libraries that you're going to use. The standard input and output and the string manipulation libraries of C are going to use, and all those libraries here come from the GNU Scientific Library. So you have the GSL fit for the linear least squares, statistics for the statistics because we're going to do covariance, correlation, and Pearson's correlation here as well. Random distribution or random number generations for the significance of the parameters or parameters, and the cumulative distribution here for the significance of the parameter. I believe this one might not be needed, but I'm just going to leave it here anyway. This here is a function before starting the program. I put this function here because I'm going to use it to interpret the significance of the parameters. In other words, if it's not significant, if the A and B parameters of the regression are not significant, if they're significant at 0.05, they're significant at 0.01, or if they're significant at less than 0.001. So this is the standard symbols using statistics here. So the main program starts here, just declaring some integer variables here for the number of variables in the array. So an integer here, and this is your data. If you want to use this data set, if you want to use this code for a data set, you just need to put your data here. I got this data for one of the libraries, statistical libraries, the .org statistics library, sort of a Wikipedia for statistics. I'll put the link in the description. I don't have it installed here right now, but I don't have it open right now. But it's just you have X data and Y data, and here you have to put the number of elements on the array. Somehow you could declare the number of variables by define here, but I rather leave it here. But it couldn't work just putting n here, but it's probably better if you put it global here as defined, but let's leave it like this. It works like this. Here are the variables that we're going to need to make this code work. I added some of my variables here for the significance of the parameters, and here is the predicted values of y for the model they're going to fit and the residuals. And all those functions here from now on, they come from the GNU Scientific Library. To be more specific, those three functions here come from the GNU Scientific Libraries. From these libraries, they're declared here. So this fits the linear regression. You put x, the stride here for x, y, the stride for y. So we're going to reading those variables here. This is the output parameters, the fit parameters C0 and C1 for the regression, the covariance of the parameters. Here comparing covariance for the covariance matrix of the parameters, and the sum squared sum squares of the residuals. This here calculates the covariance between x and y. Here, this one here everywhere is just destroyed. This is the standard correlation function, Pearson correlation. Down here I put the Spearman correlation. I'm just going to just move it up here, but it doesn't really matter anyway. So this calculates the Spearman correlation, Spearman ranks correlation. Those functions here calculate the standard error of the estimates for C0, C1 for a linear regression of the type y equals C0, the intercept plus C1, the slope times x. So this is the function that we're feeding. So the standard error of the estimates, the t-value from the t-distribution, it's the value of the parameter over the standard error, and this is the probability value for each one of these t-values. From these probability values here, we check if this is significant or not. So 2 times the cumulative t-distribution function. This p here is important because you have a key function, a q function as well. This is the degrees of freedom. Freedom is the number of variables minus 2, which is the number of parameters on the linear regression. You need this dimension here as well for the Pearson correlation. That's why I left it down here. And this prints the regression diagnostics. So the best fit model with C0 and C1, the sums of squares of the residues, the standard error of the estimates of the parameters, the t-values for C0 and C1, the probability to check if it's significant or not. So now here I invoked the significance function to check if it's significant, the significance level. Somehow it didn't work in one line. I had to split this function in 2 lines. The significance of the parameter C1 wouldn't appear correctly. This is just a print output just mentioning the interpretation. This here, this covariance matrix, this comes the standard example. I took this example from the GNU Scientific Library examples and modified putting all this here. Prints the covariance between x and y, correlation between x and y, the r squared, the coefficient of determination, which is the r squared. Spearman correlation. This here asks to print the data set on the terminal. So I modified this asking to print x, y, the predicted y values, and the residuals. And if you wish to use this value here of the code, you can uncomment this here, and this extrapolates for values, extrapolates the function. Of course, you have to modify it here. This was for the original example, but you need to modify this interval here so you can extrapolate your function for intervals below or above the interval of the data set which you're measuring. So the code it's pretty straightforward, modified from the GNU Scientific Library. Let's just get the running lines here. Just take it to the terminal. Just gonna paste it here where my C files are and run it. So that's it. This is the result. This is the regression diagnostics, best fit, sums of squares of residuals, values of the parameters, t-value of the parameters, probability values, the significance, C0 significant at 0.05, C1 significant at p less than 0.1 on 0.001. The covariance matrix, the covariance between x and y, this is the population covariance, the correlation, the r squared, and the Spearman correlation, and this is your data set. You could export this data set to wherever program you want. Of course, you could also modify this code. I could have written this code for importing external data, but this it would bring a lot of other complications that we don't need right now. Same thing for exporting the data set. I have some of the code that I showed in other videos for the numerical simulations. They import data from other files, but let's not do this here. Since I'm in Linux, I can just copy this here and paste directly on the worksheet. So if I do this here, it imports directly. I don't know if you can do this in Excel. A while ago you couldn't do this. I haven't worked in Excel in a few months now, so I haven't tested yet. And now you can do your plots. So insert here, chart. You could always do this in Python in R, export your data for Python, R, or whatever program you want. So this is the best fit line, and this is the data. So you can export for whatever you want. You could also link GNU plot or Python or whatever in this code here, and do your plot whatever you want. The advantage here is actually for learning C. It's because C it's a pretty efficient language, and most of those programs are wrappers around C or C++. So the more you learn C and C++, the better for data analysis.